This is Mallikarjun, working as assistant professor in the department of IIIE. So today we are going to discuss about a topic called steady state analysis of series RLC circuit. So up to now we have seen the different combinations like when R and L are connected in series, and then after we have come across one more combination, that is R and C. And in today's class we are going to discuss about the steady state analysis of series combination of a resistor, inductor and also a capacitor, how the phasor diagram can be drawn and what is the circuit diagram approach for it, what are the different types of impedance triangles and also the admittance triangles that can be obtained from it, what is the value of a power factor, what is the value of a phase angle. So these are the different things what we are going to learn from the today's lecture. Coming to the first slide. So this is the representation of a series RLC circuit where R is the resistor, L is an inductor and C is the capacitor. As these three elements are connected in series, the current flowing through all the elements R, L and C will be equal. That is, if I say that the current flowing through the resistor is IR and the current flowing through the inductor is IL and the current flowing through the capacitor is IC. So as these three elements are connected in series, I can say that IR will be equal to IC will be equal to IL will be equal to I. That is, the current flowing through all the elements in and out will be equal as they are connected in series. And let me say that the voltage across each element is considered as VR across the resistor, VL across the inductor and VC across the capacitor, and total voltage applied across the circuit is given as what? V. Now we will try to calculate the value of we will try to analyze the behavior of a series RLC circuit. What is the amount of output that can be obtained from it by drawing a phasor diagram, by calculating the value of a power factor and also by calculating the value of a phase angle Now we will move to the next slide. So when an AC voltage is applied to an RLC circuit, so here we can draw the phasor diagram only between any two phases that are present in a given diagram. But in this structure, in this particular circuit diagram, we have three elements that are connected in a series. That is inductor, resistor and also a capacitor. So it is impossible to draw the phasor diagram when more than two elements are present in a circuit. So due to that particular thing, we need to consider the different cases. That we will see when we are drawing the phasor diagram. Now as we know that the voltage across the inductor is represented by what? It is represented by an product of resistance and also the value of the current flowing in that particular circuit I by using an Ohm's law. And we know that the property of a resistor is current will be always in phase with the value of a voltage where the phase difference is maintained as 0 degrees. Coming to the next element, that is inductor, and the voltage across the inductor is represented by VL and the voltage is represented as VL equal to I into JXL, where XL is considered as what? Inductive reactance. It is given by 2 pi FL, where F is frequency and L is the inductance of the given circuit. And the property of the inductor is the current lags the value of voltage by 90 degrees. Coming to the one more element, that is capacitor. The voltage across the capacitor is represented by VC and in general the expression is represented as I into minus JXC. And coming to the property of this particular capacitor, current will be always leading the value of voltage by a 90 degrees if it is a pure inductor. So all these cases where the current is lagging, leading, in phase represents with respect to their own angles like 90 degrees and 0 degrees. When we are using a pure elements like pure resistor, pure inductor and pure capacitor, the angles may be varied but the nature of that inductor and capacitor are same. If I am connecting an inductor, it will try to lag the current will try to lag the value of voltage by certain angle. If I connect a capacitor in a circuit, the current will lead the value of voltage by 90 degrees. Or the same expression can also be considered as, if it is an inductor, voltage leads the value of current by 90 degrees, or if it is a capacitor, voltage lags the value of current by 90 degrees. 90 degrees. Coming to the next thing. So as I have said earlier, in order to draw the phasor diagram for a series RLC circuit, it is not possible to draw the phasor diagram representation when there are more than two elements if they are present in a circuit. So in order to draw the phasor diagram and in order to calculate the response of this particular thing, you need to consider the different cases. You need to consider the different cases. The first case is considered as XL greater than XC. XL greater than XC. And the second case is considered as XL less than XC. And the third case is considered as XL equal to XC. So depending upon these three cases, we are trying to modify the circuit at each and every point into a two circuit element, and we will try to plot the phasor diagram representation for a particular case. So when XL is greater than XC, so XL is what? Inductive reactance. XC is the capacitive reactance. If the inductive reactance of a circuit is much greater than the value of capacitive reactance that is connected in a circuit, I can say that the value of XC can be neglected. If value of XC is neglected, so what is the circuit nature now? It consists of only two elements. One is R, another one is it is purely an RL circuit. It is purely an series RL circuit. So we have seen earlier how to draw the phasor diagram representation of a series RL circuit. So depending upon the properties of elements that are connected, so what are the elements? So in under first case, it is purely behaving in an RL series circuit. So the property of a resistor is current will be in phase with the value of voltage. Property of an inductor is current will lag the value of voltage by 90 degrees. Depending upon that, we can draw the phasor diagram. As it is a series circuit, I am taking current as a reference. And according to the property of a resistor, current will be in phase with the value of a voltage. And according to the property of an inductor, current will lag the value of voltage by how many degrees? 90 degrees. And this is my resultant V equal to VR plus VL. So this is the phasor diagram representation for the first case, that is XL greater than XC. XL greater than XC. Coming to the next case. Next case is XL less than XC. That is, the inductive reactance offered by the circuit is much less than the value of capacitive reactance. Much less than the value of a capacitive reactance. So if the value of a capacitive reactance that is connected in the circuit is much greater than when compared to the other reactance, then I can say that the circuit formed will be a purely RC circuit. Purely RC circuit. Now let us draw the phasor diagram for this. As it is a series circuit, I am taking current as a reference. And with respect to the property of a resistor, current will be in phase with the value of voltage. With respect to the property of a capacitor, current will lead the value of voltage by how many degrees? 90 degrees. And this is my resultant V equal to VR plus VC. So this is the phasor diagram representation for the second case. Coming to the third case, where the value of XL is equal to XC. Where the value of XL is equal to XC. When XL equal to XC, both the reactance gets cancelled and it will be purely a resistive circuit. So what is the phasor diagram representation for resistive circuit? Current, as it is a series circuit, voltage. So these are the three phasor diagrams what we will get for a series RLC circuit when we consider the different types of cases like XL greater than XC, where it will behave as a RL series circuit. XL less than XC, where it will behave as a series RC circuit. XL greater than XC, where it will behave as a pure resistive circuit. Pure resistive circuit. So you are going to get the three phasor diagrams for a series RLC circuit. Series RLC circuit. So we are considering the cases, and this is the procedure, that is how to draw the phasor diagram. First, as it is a series circuit, I asked you to take the current as a reference. Then depending upon the properties of the elements that are connected in a circuit, if it is a R, current should be always in phase with the value of voltage. If it is a L, current should lag the value of voltage by 90 degrees, or voltage should lead the value of voltage by how many degrees? 90 degrees. If it is a capacitor, current should lead the value of voltage by 90 degrees, or voltage should lag the value of voltage by 90 degrees. Then after, you can take the resultant vector by taking the sum of the different vectors that are present in a circuit. By taking the sum of the different vectors that are present in a circuit. So this is the phasor diagram representation of one case where I am considering the value of VL and also the IR, where it is considered as VL minus VC. This is the phasor diagram representation for RL circuit. In the similar fashion, you can plot the phasor diagram representation for RC circuit, this is R. This is the, as per the property, VR I will be in phase with the value of V, and the next case, in the next case we know that XL is less than XC. That is, XC value is much greater. If XC is much greater, current should lead the value of voltage by how many degrees? 90 degrees, and it is considered as VC minus VL, and this is our resultant. This is for the next case. And for the third case, the phasor diagram representation is, it is only represented by a pure resistor circuit, that is, current will be in phase with the value of a voltage. Current will be in phase with the value of a voltage. So from the circuit representation, whatever I have taken, R, L and C, I am trying to calculate the value of a impedance. So what is the expression for voltage here? By applying KVL in the closed loop, VR plus VL plus VC. And we know the values of VR, VL and AC, where VR is indicated as I into R, VL is indicated as I into JXL, and VC is indicated as I into minus JXC. If you substitute all those parameters in the KVL expression which is obtained on the top individually, and if you take the sum, you are going to get the value of what? Impedance. You are going to get the value of what? Impedance, and impedance is represented as Z equal to under root of R square plus XL minus XC whole square. This is nothing but magnitude of the impedance. If I want to calculate the impedance directly, I can write it as R plus J into XL minus XC. R plus J into XL minus XC, where Z is the total impedance offered by this series RLC circuit, and the units for the impedance in general, it is considered as what? Ohms. Ohms. XL is the inductive reactance, XC is the capacitive reactance, R is the resistance offered by this circuit. And if I want to calculate the value of XL, the formula to calculate the value of XL is 2 pi FL, and the formula to calculate the value of XC is 1 by 2 pi FC. 1 by 2 pi FC. This is how you can calculate the value of an impedance offered by a series circuit, that is RLC. RLC. Now I am trying to calculate the value of a phase angle. As we know that in order to calculate the value of a phase angle, you need to consider the phasor diagram approach, and by using the phasor diagram, first you need to calculate the value of a tan phi. So by using the phasor diagram, the value of tan phi obtained is VL minus VC by R. Or else it can be VC minus VL by R. Both are same. These are the two values of tan phi when I am considering the different values of phasor diagram. Or else it can also be written as what? XL minus XC by R by substituting the value of VL and VC. Or else it can be what? So the value of the phase angle obtained for the series RLC circuit can be represented as phi equal to tan inverse of XL minus XC by R, or it can also be phi equal to tan inverse of XC minus XL by R under the second case. Under the second case, that is when the value of XL is less than XC, and this is the expression for XL greater than XC. XL greater than XC. Now in the next case, we are trying to calculate the value of a power factor. We are trying to calculate the value of a power factor. As we know that the definition for the power factor is, it is defined as the cosine of angle between the voltage and current. In case of a power triangle representation, it can be power used, power dissipated by the power supplied. By using that, you can calculate the value of a power factor for any type of circuit. For an RC circuit, for an RLC circuit, it is represented by, always the power factor is represented by cos phi, and it is represented by value of what? R by Z. R by Z. So as per the three circuits, whatever we have seen earlier, the value of power factor for the RL circuit, RC circuit and RLC circuit is same, that is R by Z. The Z value may be different. The Z value may be different. For the value of RL circuit, the Z is considered as R plus JXL. For the value of RC circuit, R minus JXC. For the value of RLC circuit, it is considered as R plus J into XL minus XA. The value of impedance offered by the circuit may be different, but the formula for power factor for any type of series circuit is considered as cos phi equal to R by Z, where R is the resistance offered by the circuit and Z is the impedance obtained from the circuit. Impedance obtained from the circuit. Coming to the next slide, that is applications. So there are different types of applications where the RLC circuit can be used. Sometimes it can be used as a variable tuned circuit. Sometimes they can also be used in different types of filters where it is used to eliminate some amount of frequencies like low pass, high pass filter, band pass filter, or band elimination filters, or bands of filter, depending upon the type of frequency whatever we have used there. Sometimes the same series RLC circuit can also be used as an oscillator. Sometimes it can also be used as a voltage multiplier, mux. Sometimes it can also be used as a pulse discharge circuit. Pulse discharge circuit. So these are the different types of applications of a series RLC circuit. Series RLC circuit. In the next class, and we will discuss about the other combinational circuits that are present in unit number 1 of our subject, analysis of electrical networks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.